I started, when I started creating these slides, people told me I'm going to run over. So I kind of shrunk it a little bit. So let's see how this goes. My name is Kamlesh. It's amazing to see so many people like on Saturday. This is my first Pydata talk. And I thought, like, who's going to turn up on a Saturday? And it's great to see all of you. To be honest, this is probably the time I would have just woken up on a normal Saturday. So I'm going to talk about columnar thinking, particularly around like why columnar tools are fast, like arrow polars. But then we're going to do that by like thinking of it in like three different angles. Like first is like what questions are you trying to answer, right, for analytical loads? And then we'll go into like how you need to think about like the hardware a little bit, like, you know, to answer your questions. And then most importantly, like how your data is laid out, right? So if there's anything that you would walk out from today's talk really is before you start vibe coding, you want to think about how your data is organized and what questions you're trying to answer. And through the talk, I'll go through some personal examples of like how we made mistakes and then how we had to go back and correct it. Now, obviously, these mistakes do happen. That's fine. But if you can think about these things ahead of time, you're not like going to think back, oh, I could have done this better. So by way of introduction, my name is Kamlesh Shah. I work for Morgan Stanley. I've been in Morgan Stanley for the last 12 years. My job in Morgan Stanley is I actually run a team of technologists across the globe. I've got the key function is we run the liquidity management systems in Morgan Stanley. There's sort of two aspects to that. So one is all the settlement activity that happens in that all the trades that Morgan Stanley has to settle with counterparties, they go through systems that we built. We also have the responsibility of like managing liquidities, hence the name. So what that means is we've got to work with a lot of quantitative analysts, people who are trying to optimize liquidity for the firm, and basically build tons of analytical systems that manages how we plan our liquidity over the maybe a week, 2 weeks, next year, whatever. So there's a good mix of thinking about things on a real-time basis. So we build systems that needs to run all the time across the globe, processing messages like as it happens, and also like look back and answer questions, do what-if analysis and stress tests and things like that from a forecasting and explaining perspective. Before Morgan Stanley, I've always been in like financial services mostly, like, and always been a developer, engineer, building systems, architect, and performance has always been a thing. Mostly, like, when I started, you would start with something, and then you realize like it's not running as well as you thought. Once you start putting it into a real system, a real infrastructure, and then it's always an afterthought. But then over the years, what you realize is it's not one thing or the other, right? Like it's a collection of things, and these change as well. And like what you focus on and what you're able to tune and tweak changes. Like people think like performance, it's algorithm. Like let's look at what the code is doing, what the logic is. Yeah, sure, 100%. That makes a big thing. But also there are various other things like the CPU architecture has changed over the years. So there used to be a time when you need to think about that. How many cores do you have? Now you still need to think about it, but it's probably like usually just taken care of. We've been through architectures where like there's microservices, you're moving data around all the time. Do you really care about how much volume you're shifting between these services, or like what sort of network activity is happening. Things like, for instance, serialization, deserialization, you don't really think about it at all. You just do it. And like this whole wave of agile software development meant people can just do things in isolation, and like that just brings up speed. But then you don't really think about how these services and the systems talk to each other, and who's serializing and deserializing 1,000 times, how memory is laid out. Now the fundamental thing here, though, is I mean, we've over the years like learned what sort of paradigm is really good in terms of making high performance systems. And what we've realized like over time is, like, if you just think about data in terms of columns and how it's organized and how it sort of impacts all of these dials, you'll be surprised to see really like there's a lot of strong impact on all these aspects if you have your data organized in columns. That's just not just luck or fluke. It's really, if the sort of the way CPUs have evolved, the way your memory systems have evolved, and also the way your questions have changed over time, really like reflect on how columnar storage and moving data in that column form can actually make a big difference. It's not going to hurt you. You can see like there are cases where it has a neutral impact, but there are lots of cases where it has a strong impact. So, like I said, we come from a financial services background. I've always worked in a banking kind of setup. So some of these examples are sort of like questions that you get asked from in an analytical setting. Now clearly you can apply this for other things as well, but what you will notice, and obviously I've taken like a very specific list that makes sense to my talk, but then I started doing this and I realized like actually there are many questions that you would ask, right? Like things like how at the end of the day did I fill everything I wanted to, and for what was my how did we do with the fills? Did we have any more outstanding orders? What is contributing to my price moves? Is it like the overall momentum of the market, or is it like specific stocks that's impacting it? These kind of aggregate questions, like what you realize is like you just condense all what actually happens behind the scenes, how you actually build the systems to answer these questions. What you'll realize really is that they actually fall into sort of like a few set of operations that you do behind the scenes. So aggregate, apply, group, roll, join. So these are the mix of these, and like a number of times you do this. That's really how you're answering these questions. Surely there are questions that don't fit into this, but like this is a very analytical focused sort of setting where you realize like these are some of the common operations that you perform. So the interesting thing also is that when you're performing analytical operations, the data is organized in that way, right? Like so you got your trader, your sectors, your country, and then you're performing calcs on top of it. You're calculating your P&L, you're calculating your delta. Likewise for your fills, right? These you realize are actually aggregate operations, and your data arrives in that form. You store them in that form, and then you use them in that form, right? So if you think about this, to answer these questions, like, can you just give me, the delta by sector, or like, what was my VWAP for a particular stock? You look at your data and you realize like you're not using all the columns or all the data that you have. You're very specifically focusing on, 2 or 3 columns, right? So the rest you're just there, obviously for for other queries, but for the specific things that you're actually trying to answer, you realize like you're working with a few set of columns, right? So is this columnar thing new? Is like this column oriented mindset a new thing? Not really, right? Like it's been there for the last 30 years. We started seeing it as like from a warehouse perspective. If people remember Sybase IQ, I think there was a DB2 version. I think DB2 Blue was like a column-oriented storage version of DB2. So like business intelligence warehouses. I think that was sort of the advent of how people saw reporting as a function on top of data, and like started thinking about, hey, you know what? Like actually, the reporting nature of or analytical nature of your questions need a data layout that actually serves better for that, as opposed to when you're trying to update specific rows. Then the era of big data, and that just like data became a very important thing. People started realizing having this data is such an important part of like their knowledge base, and they could do tons with it. And having data organized in a way that's easy to sort of put analytics on top of it made a lot of sense. And then you had like, how do you process that information? You had the likes of Spark coming up. We had a talk just earlier about how streaming can be done on top of like batch data. And there was a streaming era, there's a real-time streaming era that took on. And then like you had the grow even bigger, like the cloud scale data warehouses and compute systems like Snowflake, Databricks, and now like for embeddings. So this has been there, and like as you can see over time, as data became more of an important thing, the way you store it and the way you sort of perform compute on top of it became its own subject that people started focusing on and investing a lot of effort into. So in for financial services at least, I'm sure in other industries too, everyone talks about standards. Obviously the reason being, like if everyone follows one standard, you don't need to cater for a number of different things. You don't need to repeat yourselves. And clearly, like we can think of Arrow as a specification, as something that could sit across the sort of various suite of applications that you'll end up using. If you're doing things on your laptop or your virtual machine, all the way if you're deploying that to a really large scale data processing environment, as long as you've got the same format, you will realize over the next few slides that it's just not convenient. You're not just trying to sort of mentally as well as physically code for different formats. You're also getting a big advantage out of not having to transform this back and forth. So like I'm sure software engineers, data analysts, we all start with code that just looks like what you see on the left-hand side. Now the key thing is, I mean this is such an interesting thing because even experts, veteran industry software developers, managers, etc., they feel like the left-hand side is easier to read. We are used to that. There are times where I have been told by senior folks that, hey, look, focus on readability, Kamlesh. Like, even if like it's, if you want to perform and just throw the compute on top of it, focus on readability. I think like the right-hand side is more readable, right? I think the way you think about this is, and this is probably like a functional programming, pitch here, but the more expressive your code is, the better you have in terms better is your readability, but also the less you do, the less you need to do, right? So this is really where you can start over the next few slides. We'll see how polars, and you can leave like your engine to do the work when you actually just simply express what you want to do rather than focus on how you want to do it. And what I've realized is like a column way of thinking about solving or to express your sort of business logic, your calculations, just goes hand in hand with like your expressive way of actually coding. And then it also then goes hand in hand. You're not telling the engine how to do certain things, you're focusing on what you want to do, what questions you're trying to answer. And it starts to become a lot more SQL-like. The key thing here to remember is like, it's not a choice of, hey, you know, I prefer to write it like this. What you will realize is as you sort of, you know, take it from like a prototype, okay, this works, to something that you want to actually deploy in a production scale system, you realize like, you know, you're talking about order of magnitude of performance improvements because you're focusing on like the what rather than the how. So we said like, we covered the question, like what questions you're trying to answer. We covered a little bit of like how you can, you know, those questions have similar ways of solving. But then the bottom line is, like we also said, like the hardware makes a difference. So I'm sure like a lot of people have seen heard of these terms. It's pretty common to talk about these in the universe of polars, right? But the key thing is what we need to realize, like going back to history, is alongside how like, you know, data became an important thing. The other thing that kept happening is like your CPU became more and more faster, right? And then like the memory side of it, unfortunately didn't, right? So as CPUs become faster, what happens is your bottleneck really becomes how do you actually give it the data to process, right? So cache locality, and we'll talk a little bit more about it, becomes an important thing. So it's like, you know, you've got a builder in your house, and they're doing they're up there for a construction work. If you think about it, like a good builder, the way they start the job is, they don't start it immediately. As soon as you say, I need this thing done, they don't come and say, yeah, I'm going to do it. They say, I need some time. They go and prepare for it. They're ordering goods. They're ordering things like bricks and all the stuff they need to do the building work. And then the first day they're going to start the job, what you see is they actually bring all of this stuff and keep it next to where they're actually going to build. If they're going to build a wall, you'll see a ton of bricks, right? So they're trying to keep what they need close, and you know, sense is like the closer that is, the easier that is to access, the faster they're going to be building. So that's your your cache locality concept. Obviously, SIMD, a lot of people might have heard of it. This is like, you know, using your cache lines efficiently, but also using the CPU efficiently. Instead of doing one thing at a time, can you do many things at a time in one shot? And you know, today's CPUs are like, you know, they're catered for that kind of stuff. So the more you let them be good at that, the faster is your processing. And again, like, you know, bringing that data closer to the CPU, those things become a bottleneck, like your memory bandwidth. So we spoke a little bit about like the keep bringing the data that you need closer to the CPU, right? So CPU, the way memory works is like, you know, for people who might not know, is like, you know, it's collection of cache lines, like level 1, level 2, level 3 cache, and then your main memory. The CPU spends lesser time fetching this information, the closer the the caches. And also, the amount of information you can store is lesser and lesser as you get closer to the CPU, right? So if the bottom line is if you put information that your CPU doesn't need or it's not going to use closer to it during your processing cycles, you're wasting your memory. And the key point here is the more you do it, the order of magnitude of the time that you're going to spend just fetching information is going to be larger, right? So keep things close. The CPU also is good at prefetching. So again, like using this builder example. So if someone's like laying bricks to build a wall, they're obviously going to be faster if someone's handing them the bricks. Now, if the builder's going to just use the bricks and so they're just being handed these bricks, great, they're going to be most efficient. But if like, imagine this person who's handing the bricks to the builder decides to like have to search for other things among the bricks and like then find the bricks, then it's going to be slower, right? So the concept really is like arranging your data in a way that's easier for you to sort of prefetch, for the CPU to prefetch, makes a big difference. So if you look at the left-hand side, for analytical workload, you've arranged your data in such a way that if you take, it's basically the CPU needs to search among 4 things to find the price, for instance. Whereas like on the right-hand side, you've arranged the data in a way the CPU can just take it and perform that operations in a bulk manner, which nicely sort of lines up with the SIMD concept, where you can do many things in one go as opposed to just like focusing on one thing and then moving on to the next. So this is like, just very, very, very key factor of like how you can actually use your CPU to do better, just purely like by organizing your data in your memory in a way that is very conducive for it to do well. So if you think about like this slide here, the left-hand side is actually telling you like if you just want one information, you're gonna have so many cache misses. So you're wasting. If you look at that levels of cache lines that you had, you're wasting opportunity you're filling it with information you don't need. That's the bottom line. You need to fill it with information that you're going to use so that that prefetching concept works very optimally, and also like the concept of and it being SIM ready, right? SIMD ready. The other thing column stores are really good at, and like you could see some of the industry standard data warehouse providers use these very, very this is a common pattern for them. It's like, it's easier to compress a column because it's all data of the same type. So you could use different compression algorithms that are more suited for a specific data type and cardinality, right? Whereas if you try and do the same thing with a row, then you can only get as efficient as you can because they are different data types, and you cannot use like the most optimal compression algorithm to effectively like compress them. So columns are naturally column-based stores are naturally sort of lend themselves to be better at compression, right? And again, that just means what? Like that really means like your I/O. When you decide to move data around, that gets cheaper, right? I'm sure like disk is cheap and all that, but still like you're trying to take that and load it into memory. Small is always better. The more you can do that, the better it is for you, right? We mentioned SIMD. This concept's popularly called vectorization, right? So it's essentially like if you think about the scalar concept, it's like you basically just take you perform operations one at a time against a subset of that information. So you take A and you take B and you add them together. So what happens is a loop mindset. You go through a list of these values, and you kind of like approach that in a scalar fashion. Again, you're not using the CPU to its best, right? Like with some of these CPUs here, you can basically see that you can have like you can fill the cache lines with arrays of this information, and you can perform these calculations and aggregate in batches. This makes a tremendous amount of performance improvement. You could see some speed up metrics here when you have like a 32-bit floating point operation, data types. You can fit up to like 16 of them in one go on AVX 512, and that means like you can perform same operation across that many batches, and the CPU just does it for you. Right, and there's also it's not a very Polar specific thing. Like there's tons of other Python based libraries that gives you this. Some of them specialize in that, but the concept is you could still achieve that to its best capabilities if your data is organized in that fashion. But you're also thinking about it in that way. So, like, do we need to be worried about this sort of stuff? I think that's like, yeah, sure, you should be aware of it, because this is how the system works. This is what makes it better. But again, like I go back to the whole expressive way of doing things. If you allow the engine to take care of doing the work, and you are just basically using expressions to define what you want to do, as you get like, this is economies of scale, right? Like, as like these CPUs get more powerful, and I'm sure like the memory, the storage, and the bandwidth concepts are going to follow through. And there are these like engines like Polars, for instance, and others, the PySpark and Spark, and they take care of how to most optimally manage and get the most out of your hardware, rather than you trying to sort of, if you're in a business of like, providing solutions as opposed to working within these engines, you're better off just like expressing things in a way where it's conducive for these engines. So again, columns help here, and then the way you're describing your problems help as well. The planning is an important thing. Again, like for people who are very familiar with Polars, you realize like there are ways in which Polar's pretty smart in the way in which it evaluates these operations ahead of time and reorganizes the operations for you, decides on what to put first versus not, what to push down all the way down to the data read level, and all the tons of other optimizations, the parallelization that it can do. All of that comes when you actually just express what you actually want to do rather than focus on how we want to do it. Like the famous, I'm sure for people who've been in the industry for a while writing software is, there's obviously, when everyone starts, the cool thing to do is write multi-threaded code. Like you love multi-threaded code because it's complex, but it's very hard to get it right. It's very hard to get multi-threaded code right. And one of the first things I tell developers who are just like, starting off and like trying to do this is like, there are no specific, nothing specific to you, but there are people whose day job is to make that multi-threaded code very, 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 very good, and they're experts in that. Leave that to them and focus on like the business logic. Focus on what you're trying to solve. Polars is obviously a very good example for that. It supports this sort of concept right from the beginning. I've just been told I only have 5 minutes, so I'm going to rush a little bit. This is where the whole slide organization, someone told me I should, yeah. So Polars has this concept of different ways of execution, right? Like you've got your ego way, which is like your usual way of processing. It's great if you want to like step through and debug and things like that. You've got the lazy way of operating, which you give the engine the ability to go and plan and optimize. Amazing. And then you have the streaming concept where, if you really have a lot of data that you cannot fit within your memory, then you could use streaming, and Polars takes care of that. When you're like working in a tight system where, you're trying to prove the concept within you're not deploying this on a cloud scale, and you're like working locally. I wanted to give a few examples of like where columnar just makes sense out of the box. So here's an example where you could apply columnar end to end, right? Like historical VAR, you basically look back at price movements over a historical period. You take your current portfolio, whatever the weights you have with your current portfolio assets, you go back to the returns that happened in the past. You reapply those returns on top of your portfolio with weights. You then calculate your P&L on top of it, and then you take all the output, you order it, and you basically say like, what was my 1% value at risk or 5% value at risk? All of this is like end-to-end columnar. You don't need to think about loops. But the funny thing is, when I actually went and did some research on this to see like, hey, where is that? Just like, who's done this? Can you give me some example code? I like went across like 8 or 9 examples, and I think just 1 or 2 of them used columnar. Every other example that you see there at the moment is just using loops, right? So hence, like this talk. I hope this was useful because this is a column-based. It's just out and out, a candidate for column-based approach, and the speed you get for that kind of thing, you would not get for loops. And again, going back to my thought about expressions are easier to understand than loops. I don't understand why you still have all these loopy examples out there, right? This is again, just a quick example of how the code could look like for your column-based approach. The thing is, it's very, very close to how you would do SQL, right? So the funny thing is, like, you could even call Polars as like a way to talk to your data frame, right? Instead of talk to your data. I hope people know what talk to your data is, like with the all LLM and AI-based talk to your data concepts. So now, is that like a consistent sort of thought process? Like, is every problem going to be a column-based problem for you? Not really, right? Like real world examples. So like, for example, if you're going to do a Monte Carlo simulation, as people may know, there's a part where you've got to calculate the tomorrow's price using using stochastic calculus, geometric Brownian movement. So you need to know what today's price is to then to calculate tomorrow's. Now, depending on the asset that you're actually simulating, you may, if it's a complex exotic option, for instance, you may need to go back and not just like the today, but also look at all the historical predictions you've done and average or perform some operations on top of it. These are unfortunately loopy operations, right? You've got to do it. It's a loop. You don't have a choice. But the key thing here is, again, if you understand how the hardware works and if you know how CPU helps you, then you could use tools like Number, for instance. Number is like a just-in-time compiler, which is really good at taking loops and vectorizing them all the way down at the CPU level. So again, concept is you don't need to think about it. You could use these amazing tools to make your code really, really fast, while algorithmically certain things are confined to loops. But again, that doesn't mean everything needs to be loops, right? Like you use loops where you need to, and then you transform to, again, columnar, where it makes total sense. Again, this slide's basically telling you how you can stitch these things together, right? Like you've got basically number on the left that gives you sort of a NumPy array and then you could turn that into arrow, and then you have all the columnar operations that can follow after that. Zero copy is a key term, right? The concept is you could just use the same data format across the board. You're not really transforming it to a different format. Such an important thing when you're looking at like scalable systems. So there is a spectrum of these, right? Like stress tests are particularly like hard to run in a column fashion. We've been struck by that. Like we've had like, hey, you know what, distributed processing, let's take it and like have Spark run all of this for you, amazing. But then it's slower than how my Java application was running. Why? Because it's not a problem you can solve purely by scaling and distributing. It's a loop kind of a situation. So you need to it's CPU bound, right? Whereas there are other things like P&L calculations which are very vectorizable. So there's a spectrum. The point here really is think about what you're trying to answer, going back to the questions, and how your data is laid out, right? You can, again, zero copy again, right? Like, so if you think about how your data flows end to end, you start with your data coming into your databases. You have an engine that's processing them. You need to move it to show to on a user dashboard, etc. You can do the whole thing using Arrow, right? Arrow Flight is another way in which you can actually have the Arrow format go all the way through your pipes, your network layer, right? So again, basically, it's the same concept. You expressed your code, your business logic. It works across. It's not the same code, obviously, but if you're vibe coding, right? You just have to think about it like your thought process remains the same. The way you group by, you aggregate, etc. And it can run on PySpark, can run on Snowpark. And Arrow is a format that can work across the board. All right, last point. Key things, right? Think about your data layout. If it can be modeled as a column, prefer that. Express your business logic. Don't worry about how to do it. Let the engine take care of it. Use the engine's capabilities to be lazy. Think about how your underlying engine would optimize your expressions. Loop where you need. Try and keep a consistent format for your data, like Arrow. And store like you compute. Columns first, folks. And then code.